We now look at electric potential between parallel plates, or we can say for a uniform electric field. Uniform means that the electric field lines are parallel and the field is uniform everywhere, a uniform electric field. So if we take two parallel plates and they are large compared to the distance between them, let's say the distance is d, and we have a positive charge on the left plate, a negative charge on the right plate, we can do that by attaching this to a battery, the positive terminal to the left and negative terminal to the right, and there is some voltage in this battery. The electric field will go from the positive towards the negative, and it's uniform. Now the equation that we have was that the potential difference between A and B, where A is this plate and B is this plate, is going to be minus integral of E dot ds from A to B. Now the this is our x direction and that's the y direction. The electric field is going to be E, magnitude of E, in the I direction. So the electric field is towards the right, it's in the I direction. And dot ds, which is going to be dx, and that is also in the I direction because we want to find the potential difference between A and B, so it's B minus A, so we're going from A towards B. That's also I. And so I dot I is simply 1, and we have a negative here. The electric field is uniform, which means it's constant, so it will become E integral of dx, which is Ex, and the limits from A to B. So it's simply going to be minus E x of B minus x of A. So, or that is simply the distance d, E times d. Now, if we don't go from one plate to another, but the point A is somewhere here and the point B is somewhere here, then, well, this will be our distance d. If this is A and that's B, then it's the same thing. And the electric field is everywhere the same, so it doesn't matter. Now, this equation, delta VAB, can also be used to obtain the electric field between parallel plates. So we can say that the electric field is the potential difference over D with the minus sign. So the potential difference is the voltage of the battery, or the potential difference of the battery, which we know, and D is the distance which we know, so we can calculate the electric field. So let's do an example, and we'll take the distance D as 10 centimeters, and we take the delta V, or the potential difference here, as 3 volts. So this is the negative, the small one is always the negative, and that the positive. The difference between these two is 3 volts. You can say that this is 0 and that's plus 3, or you can take them in any other way, but this would be plus 3 compared to that. And now we'll substitute these in here. The electric field is going to be the negative of 3 volts over D, which is 0.1 meter. That's going to be 30 volts per meter, or 30 newtons per coulomb. Now, what to do about the sign? Well, if you're going from here to here, the voltage is decreasing. From A to B, the voltage is decreasing, so it should be taken as a negative. We're going from a higher potential to a lower potential, and so we should have added a negative here and another negative here, which makes it a positive. So the electric field is 30 newtons per meter in the positive x direction. Now let's take the same example, and this time, or same two plates, we have a potential difference of, let's say we'll take some potential difference, let's say the same value that we had before, and we have an electric field here which we take as what we found earlier, so that's 30 newtons per coulomb, and this is the positive and the negative plate, and we take over here, we take an electron and we release this electron over here, so the negative plate will repel it, the positive will attract it, there will be a force on the electron which will accelerate it towards the left. When you have a force, you have an acceleration, F equals ma. So the force is going to be the charge of the electron times the electric field. This will be the mass of the electron times a. So the electron will have an acceleration equals e over m. And as it accelerates and reaches here, we can find the velocity over here, and we can find the kinetic energy over here. So let's do that. Let's find the kinetic energy of the electron as it reaches the other plate. So what is the kinetic energy over here? Now we can do it this way, get the acceleration and use the equations of motion and get the, we could say v final square equals v initial square plus 2a delta x. The delta x is the distance between the plates, the a we get from here, and the v initial is 0 if it starts from rest, so we can get the v final, and so we can get the kinetic energy. But let's do it in another way. Let's do it by using the energy balance equation, that is delta k plus, and that's the ke, kinetic energy, plus the delta ue, and there is no other force here. The gravitational force is downwards and it's negligible compared to the electric force, so that's going to be equal to 0. The delta k is going to be k final minus k initial, so k final is here, k initial is here, and that equals, and that the delta ue is minus qe dot ds. Okay, so it's going to be a negative qe ds equals 0. So now let's solve this part separately, see what this gives us. So if we're going from here to here, so that's our point A and that's the point B. So we should do that from A to B. And that becomes, let's keep the negative here, the Q is the charge of the electron, which is electronic charge, and the electric field is this way, so it's in the positive direction, so it's EI, and the ds is from right to left, so that's a dx with a minus I. Now the negative with a negative will make it a positive, and I dot I will make it 1. So k initial is 0, so we will have simply k final equals this minus equals 0, and so the final kinetic energy is going to be, if we take this on the other side, the two negatives make a positive, we bring it on the other side, becomes a negative, the E is constant, an integral of dx from A to B, so that's simply minus QED. Now let's plug in the numbers. So Q is minus 1.6 into 10 to the power minus 19 coulombs. That's the charge of the electron. The electric field we take as 30 newtons per coulomb, and the distance is, we take it as before, which is what we had here, 10 centimeters, 0.1 meter. The coulombs will cancel, a Newton meter will give us a joule, so the units come out right, and when we multiply this, we will get 4.8, and with a positive sign, into 10 to the power minus 19 joules. So that becomes the kinetic energy of the electron as it hits the positive plate. Now let's do a small change. Let's change the voltage to 1 volt. So instead of having 3 volts and getting 30 newtons per coulomb, if we had 1 volt, then what would we get? Well, the electric field would be 1 over 0.1, so that's going to be 10 newtons per coulomb. And so our potential energy, our kinetic energy that the electron will have, Ke of the electron, this is if delta V is 1 volt. That will be, using the same equation, it's going to be 1.6 into 10 to the power minus 19, and this will be 10 newtons per coulomb, and that will be now 0.1 meter, and that gives us 1.6 into 10 to the power minus 19 joules. Now this particular number is called an EV. It's called the electron volt. An electron volt is a unit of energy. And when we want to find the energy of electrons or other elementary particles, we usually give it in terms of the electron volts. How much electron volt does that particle have? So for example, when carbon combines with an oxygen molecule and makes CO2, it releases about 30 electron volts of energy. So one molecule burning, one carbon atom burning, will create about 30 electron volts. And similarly, the energy of the electrons going around an atom, so when they move up or down a level, the difference between these energies is of the order of a few electron volts. It could be much bigger if it's going from a lower level to a higher level. Then it could be a few, even kilo electron volts. That's how we get the X-rays. So an EV, one EV is so many joules, and it is a unit of energy.